Homework 2.7, Inverse Functions, Video 6. Homework due Friday, May 22nd, 2020 at 11:59 p.m. This final video in this series will cover topics associated with questions 12 and 13 on Homework 2.7. So to wrap up this discussion, I want to talk about the relationship between the graphs of a function and its inverse. And we've kind of already seen one example, but I didn't dwell on it at the time. Recall that when we first looked at f of x equals x squared and what was g of x equals the square root of x, they weren't inverses because there was a domain range mismatch. Namely, if we square a negative number, we can't get it back from the square root. But we fixed that by restricting the domain of f of x equals x squared and not allowing it to take in negative numbers. So any number we do put in, we can get back. The effect of imposing this restriction on the domain is instead of being the entire parabola, it was just the right half of it. So the graph of the squaring function, at least the right half of it, looked like that. But do you remember what the graph of the square root function looked like? It was the same shape, except it was the top half of a parabola opening to the right. So the one on top, and maybe I should have used different colors. Give me 1 second to reset these in different colors. That's why I have them. So we'll do f of x equals x squared if x is greater than or equal to 0 in red. So that was the right half of your standard parabola. And we'll write f inverse of x equals the square root of x, whose graph was the top half of a parabola opening to the right. There's a relationship between these two graphs. There's a line of symmetry in the sense that one of them is the mirror image of the other. Do you see where the line of symmetry is? It's not the y-axis. It's not the x-axis. It's this diagonal line. This diagonal line has a slope of 1 and a y-intercept of 0, meaning its equation is y equals x. Think about that. It's not a coincidence that the graphs are mirror images across that diagonal line, the graphs of this function and its inverse. Because think about what a function and its inverse are supposed to do. For example, let's take these two functions, and I'm telling you that they're inverses. F of x equals 2x plus 1, and f inverse of x equals 1/2 x minus 1/2. If you don't believe me, either do the composition in both directions or go through the procedure in the last video to find the inverse of this function and you'll get that one. Actually, you'll get this one, but I split it into two to look like slope-intercept form. Speaking of slope-intercept form, let's use the slope-intercept form of f of x to sketch the graph real quick. The y-intercept is 1, so we can put a point here at 0, 1. And because the slope is 2, we can interpret it as 2 over 1. And by interpreting it as 2 over 1, that means I can rise 2 and run 1. So if we rise 2, I'm trying to get different colored markers here. If we rise 2 and run 1, that will put us at this point. I believe that point is 1, 3. And we can draw our line. Looks like that. But what would the graph of the inverse look like? Well, stop and think about how the inverse is related to the function. When I say the point 0, 1 is on the graph of this, that means if I put in 0, I get out 1. That's easy to check. Put in 0, you get out 1. But what should the inverse do? The inverse should take the 1 and turn it back into a 0. And we can check that real quick. Put 1 in here, you'll get 1/2 minus 1/2 is 0. But the whole idea about inverse functions is if you put a number into the first and get out the output, the inverse function should take the output and turn it back into the input. Which in terms of the graph means if 0, 1 is on the graph of the original function, then 1, 0 should be on the graph of the inverse. And it is. Check it. Put in 1, you get 0. Would that work over here? It would. Saying 1 comma 3 is on this function's graph means if I put in 1, I'll get out 3. You can check it real quick, it is. So this function will take a 1 and turn it to a 3, which means the inverse should take a 3 and turn it to a 1. You can check it. Half of 3 is 1 1/2, minus 1/2 is 1. So, if 1 comma 3 is on the graph of the original function, then 3 comma 1 should be on the graph of the inverse function, and it is. So every point on the graph of the function has a corresponding point on the graph of the inverse. You simply find that point by switching the coordinates. And if you switch the coordinates of the point, 1 comma 3 to 3 comma 1, you get the mirror image across that diagonal line, y equals x. So in your homework on these two questions, one of them asks you which of the following is the graph of the inverse, or here's the graph of the function, which one represents the graph of the function and its inverse, and the answer is you just draw its mirror image across this diagonal line. But one of them actually asks you to draw the graph of the inverse, and in order to do that you have to locate points and reverse their coordinates. Now wait a minute, I wonder what this point is. It seems to be on the line y equals x, but it's its own mirror image, which means that when I switch the coordinates it stays the same. I wonder what point that is. I'm just thinking out loud. You don't have to find it, but I think I already found it. I did. I wonder if you can find it. All right, that's the end of this video series. See you in the next one.